all the standards activities that we do here, including documentation, will be posted on that website. All right. So, like if anyone heard, Craig Slenoff, who's leading the standards, is in one of the lead positions for IEEE standards development efforts. I talk about grasping and manipulation benchmarks. There's lots of work being done out there. And I think this group is the ideal place to form a working group where not only we produce these end effector type performance measures, but there's lots of other work that we can accomplish together, and bring in additional colleagues who are interested in particular topics as we go. But let's talk about why NIST started pursuing these performance measures for robotic hands. It turns out that our prediction is in the future, there'll be lots of small manufacturers who in the US, make up more than 90% of the manufacturing base, will incorporate robots into their environments. These small and medium-sized manufacturers typically operate in small batch sizes. Unlike the big manufacturers like Ford Motors, General Motors, GE, their production runs are relatively short, maybe over the period of a month. And in order to accomplish their mission robotics, they'd have to do a lot of retooling to accomplish their batches. So lots of tooling changes, and that is cost prohibitive. While robotic hands now are sort of cost prohibitive in a lot of factors, and they're not quite ready for the market, we can see that if there are a good supply of robotic hands on the market and the prices come down, that they will help to drive robotics in these small batch manufacturing operations, and there's a lot of potential customers for these types of systems. So the problem is, so what makes a good hand or gripper? And like I said, we need to inform the consumer somehow through specifications of how well these things operate, and under what instances they perform best, so that you can choose the right one for the intended application. So like I said, initially, I think all this work will not go unused. We'll have some really good benchmarking tools for the research community, and then eventually technical specifications. And so the mechanism that we've used, and I'll go over what we've done so far at NIST, we develop metrics and test methods. And along with those, we have artifacts and data sets. And along with that, we also have some guidance on how to analyze the data. So all this, I think you saw in my email, I sent you a link to the first document here, Performance Metrics and Test Methods for Robotic Hands. You can see that we changed the name to end effector technologies. We don't want to limit the use of these performance measures. While we did develop them with our focus on robotic hands, there are a lot of potential uses for other end effector technologies. So we don't want to leave anybody out. Anyway, there's these two publications that summarize the work we've done till now. This work stopped in 2018. Since 2018, we've probably seen about 50 or so references to our work, our publications. So that could be potentially good feedback, as well as this group, on how to improve these performance methods. And there's two documents here. The other one is something we started just after finishing the test methods document, and that is some terminology, because we all need to speak the same language. While for the standards effort, all the terminology might go in the same document, it's good to have a good understanding and be on the same page with regard to terminology. And below is a link for that documentation. So these elemental performance measures to support robotic hands were developed, and right now there's 11 of them. Here they are listed, anywhere from force-based finger strength, touch sensitivity, finger force tracking, force calibration. In the NIST laboratory, we used a 6-axis force torque sensor to make our measurements. Finger repeatability, we've tried a couple of methods. We used a simple machinist gauge to do the measurements because of the precision. The hands we happened to use had really good mechanical mechanisms and motor drives, so the repeatable was in the order of a robotic arm. Whereas we also tried using motion tracking systems to measure the repeatability, which might be useful for something such as a soft robot hand. It depends on the resolution of the repeatability. So you have to have a measurement device that measures much better than usually we say 10 times better than the system under test. We also have other test methods such as grasp strength, slip resistance, grasp efficiency, and cycle time. To perform those tests, we developed this split cylinder artifact. We really only experimented with one size cylinder, although we suggest testing over a series of different diameters. All it is a plastic printed core with PVC piping overlaid on top of it, and it's sandwiched in between it are a couple of single axis force torque sensors, and likewise uses single axis force sensor, and likewise we use if we're pulling on it for the slip resistance and grasp efficiency test, we put an additional sensor in there to measure how hard we're pulling on it. And other tests include in-hand manipulation and object pose estimation. So what I'll do is I'll step through these relatively quickly. If you're going to be part of this group, you're going to have to read the document, become familiar with what we've done so far in order to suggest improvements and help us to document these the best that we can. So finger strength measures the maximum force a robot finger can impose on its environment. We measure the peak quasi-static forces with a load cell at full finger extension. And when I say quasi-static forces, we define how to measure the forces. We get rid of the initial impact forces and things like that, and describe to the user how to extract the data. And why do we do this measurement? The strength across fingers can vary. It's the weakest at full extension. That's why we tested full extension. This is correlated with a payload as well as guide control. Grasp strength, the maximum force a robot hand can impose on an object, artifact with intrinsic. So we use the split cylinder artifact, and it's a good way to estimate payload. It takes into account the frictional properties of the hand at maximum closing strength. And we've seen these tests used. So these first tests I'm going to go through are going to be the ones that I suggest that we maybe start with, because they're more of the basic tests. And there's been a lot of usages in the research community already, so we could draw off of the work that's been performed. Here's slip resistance. What's the maximum force a hand can sustain in shear? Maximum peak force at the onset of gross slipping. This is a test that Lionel Berglund used up in Canada when he was developing his grippers, and he had some really good suggestions of how to improve the test method, which we have documented, and we will include those suggestions along with other suggestions when we address this as a team. Anyway, this is a good indicator of, so this is a measure of the peak force at the onset of gross slipping. So not micro slipping, but when you really can visually see the thing slipping. It's an indicator of minimum payload, an indicator of whole hand friction coefficient, safer to test. yeah. So sorry, the previous one is really what I was talking about here. This is just how much force you can close your hand at, and you can estimate the payload based on that. So cycle time is another. You know, activity is important, especially in manufacturing. So we want to know how fast you can complete a grass cycle. And you could do this using the split cylinder artifact by uh, providing a couple of cycles and measuring the time between cycles, starts and stops. Uh, this finger repeatability is a relatively new uh, test that we developed maybe just last year. It might even not be added to the document yet. Um, so this is very similar to what we do with robot arms. You know, we move it through a series of motions, and we see if we can land at the same position every time. Repeatability is really important in robotics. Um, it does require 2 consecutive cycles with a force sensing object artifact. Not, no, I'm sorry, not a force sensing object artifact, but position sensing artifact. Sorry. Um, so we're measuring the ability to reestablish pose. And as you can see, we just reset it in the video. We come back in, you know, this is the shunt dexterous hand, and you can see it comes back to the same uh, zero position every time to within, I think we're measuring in perhaps thousandths of an inch there, I'm not sure. Anyway, the point here is okay. So let me mention too. You'll see some test implementations by NIST using various robotic hands and measurement systems. And we're not endorsing any of these. We don't necessarily say any of these are the best product for doing that test. Um, it's up to you to determine that you know, you're choosing which robotic hand you're testing. If you're not developing one and you're just trying to choose one, NIST is not going to recommend what robotic hand you should choose. We'll never do that. We're just developing the test methods. And we don't necessarily develop the best measurement techniques, although we try to, like I said, come up with measurement techniques that can measure at least 10 times better than the system performs. Okay. So yeah, measuring the ability to establish pose, just like robot arms. Um, Touch sensitivity is an important one. So someone mentioned that they're working with tactile sensing. So these test methods support tactile sensing and their integration into the control of the gripper, the grip controller, uh, whether it's positional or force. So we're trying to measure the smallest self-registered contact force exerted by a robot finger on an object. And this is important when you go to pick up a part because you don't want to disturb the part. You want to get all your fingers in contact before you apply your grasping forces to move the part. So we do this again at full finger extension. Um, in here, you know, I don't think we got into these details, but this is something the group could work out, is some specifications on speed, maybe perform the test at maximum speed, and then a speed for to establish the best lowest contact force also. It's hard to say, you know, a lot of it's left up to the user on how to measure their system. Uh, so there's a lot of variables involved. The thing is when you're comparing research results, you need to all be on the same page in order to make comparisons. So it's important as a group that we try to come in on a specific set of parameters to go along with the test method, so everyone could compare results efficiently. Grasp efficiency, you can see we don't have a video here. We have not done an implementation at NIST, but the idea is when you grasp a part, just like we do, you don't grasp it with all your force. You grasp it with the amount of force required to resist external forces. But if those external forces change, you need to you need to modulate your force control in order to make adjustments to prevent slipping. So the idea is if you can sense slipping through your tactile senses, you can adjust the force of your grasp to prevent that slipping and measure how efficiently your control system does that. Be really interested if anyone has an interest in trying to implement this, that would be great. Finger force tracking. So so it's a finger's ability to impose the desired contact forces on its environment. So here we introduce a sinusoidal type um, control scheme to maintain a force profile on this object. So we're measuring it using a 6-axis force torque sensor, and we're comparing it to what the hand thinks it's doing as far as its force feedback. It has a lot. It has a pretty big tie into calibration. Also, you'll see offsets in the curves. You know, complete offsets if your calibration is off. And likewise, here's force calibration. So they go hand in hand. And then in-hand manipulation is the ability to measure a robot's hand to control the pose of an object. So what are your limits? Uh, we do gating here, but there is an interest in gating and determining how well you can manipulate an object using gating. So that's open for test methods also. We use a motion capture system with optical targets and primitive shapes, cylinders, spheres, cubes, things like that. These are all plastic printed parts. And it quantifies the range of motion, frequency response, controller accuracy, and repeatability. And this is very useful for functional level tasks to perform these baseline tests anyway. And likewise, when you manipulate an object, you want to make sure that you can tell where it is relative to your grasp in order to do something to achieve the positional accuracy to perform a task. So we have this object pose estimation. Can the hand estimate where it is in the grasp? So as you manipulate it around in grasp, then you know where it is relative to your grasp. So that pretty much concludes what NIST has done over the years. It was a pretty quick summary of each of the test methods, but if you go into the documents online, you'll be able to read the details. You can implement them, and you can come up with new ideas of how to improve them. And this is what everyone's done so far. Most of that work was done through an robotic hands grasping and manipulation technical committee under IEEE. So we had some pretty good input under there, but it was very early on in the effort. So now that this publication's been around for a while, and people, like, I think we have about maybe 50 references to our work where there's been experimentation associated with someone's research, and they tried to implement these test methods. So now that we're at that state, I think it's a good opportunity for us to review that work and try to make some adjustments through this group to home in on a more formal set of test methods that we can turn into a standard that everyone can use. So here's some other publications for the work, including the NIST SP documents that house all the test methods and terminology. And I think I'll save the discussion. Let me go back up here really quick to our agenda. And next we're going to have Adam Norton talk about the Nerve Center and what they do and their test resources. And he's going to try to coordinate in this activity, he's going to try to coordinate everyone's work to implement the test methods and provide feedback in their own laboratories. Because I'd really like to see, you know, a good 2 to 3 implementations per test method outside of NIST. and gain feedback on that. So go ahead, Adam. I'll let you take off. And I guess I need to stop sharing, and you should be able to share your presentation.
Let's see here.
And while Adam's getting ready, I should mention, within the special publications, when we first started this work, we did a literature search. While they were hard to find, we did find some pretty good work that we leveraged when we developed these test methods. And that's all referenced in that special publication, this publication. So you can see where some of these test methods first came to fruition.
All right. Are you guys seeing a PowerPoint slide?
Yes.
Wonderful. Okay. Thanks, Joe, for the intro, and happy that everyone's able to gather here today and moving forward for this effort. So again, I'm Adam Norton from the University of Massachusetts Lowell, the Associate Director of a research facility called the Nerve Center. And what I'm going to talk about for today is the various efforts that we're involved in to do with robotic grasping and manipulation test methods, and some of the resources we're either developing or that are already available, and kind of practices that we can glean from some existing efforts in this IEEE study group. Just as a quick plug for the Nerve Center, for those who are not familiar, we are an interdisciplinary robot testing, research, and training center that is focused on the different ways you can evaluate robot capabilities across many different domains, including response robots, industrial automation, exoskeletons, and trying to expand that further now into things including unmanned aerial systems and the like. Our director is Holly Yanko, who's a noted HRI researcher, and we have a slew of affiliated faculty across many different domains. But the one I'm going to focus on today is all on robotic manipulation. And at the Nerve Center, while our focus is on the development of test methods and metrics and evaluation means for these types of systems, we have to have a slew of candidate robot systems we can use for development. So what we have been developing over the past 2 years is this Armada industrial manipulator testbed. And that also includes some mobile systems that either have manipulators or could be outfitted with manipulators. And it's a testbed we've been building such that we can replicate a variety of different types of manipulation scenarios, whether it is more industrially focused arms, more collaborative focused arms, and developing infrastructure so we can change in and out the various end effectors and sensor systems that those arms use to get a kind of spread of capabilities across those different systems. And this is really important for developing the types of test methods and performance metrics that we do, because we want to have a wide range of capability that's going to apply to a lot of different areas. From a high level, the various efforts that we're involved in go from kind of the elemental grasping with some of our work with NIST that Joe was just talking about, as well as some of the task boards used for assembly, up to human-robot collaboration. We also have some other ongoing efforts that involve taking some of those test methods and making them remotely available through a collaborative NSF grant with Oregon State University. And in the past year and a half, we have taken over the distribution of the YCB object and model set that I know Burke is going to talk a little bit about later. But kind of a way to think about this kind of spread of test methods that are available, or they're at least in development, is they kind of increase in complexity, going from your kind of basic end effector capabilities, so more kind of the properties of that system, more kind of basic coarse object grasping, more finer object manipulation, say with use of some of the YCB object set objects, and then much finer task object manipulation for the NIST assembly task board. And I put this up here just to show that I assume that kind of within the scope of this group that we're looking at kind of everything that falls within this range of complexity, and probably further, because nothing in here explicitly relies on tactile sensing, for instance, but definitely could. So just kind of an example of how we will take some of these existing test methods and other efforts and kind of harden and strengthen them through our process. If we take, for example, on the total left end of that complexity spectrum, the grasp strength and cycle time test method that Joe was talking about earlier, which consists of these various split geometry artifacts with load cells inside that you can use to evaluate their end effector capabilities. So for this test, in the way that it's currently scoped within that NIST document, it has all of the protocols and kind of artifact elements that you need to adhere to. And collaboratively with NIST in a paper that was published this year in the IEEE RAL special issue on benchmarking protocols, we really expanded that process to better kind of capture the various different artifacts that you can use, expanding that to be cylinder geometry artifacts and block artifacts, considering the different grasping forces, orientations that you would use, and providing tools to make some of that testing easier. So 3D models available of many different types of artifacts in all different sizes, software for extracting the different quasi-static force readings for grasp strength and timing that Joe was alluding to. And that's available at this tiny URL, which is also linked in the paper that is, I believe, is available as open access. So kind of moving further up in that line of complexity is the YCB object and model set that I won't spend too much time on because I know Burke will be talking about it later, but just as a mention that it is, I believe, probably the most widely distributed set of common objects used for research, with over 200 kits distributed internationally to date. That's not just from as we've taken them over. I think that's about 50-50 between prior to us taking over the set. And something that I just want to mention here, because some of the people on this call may have YCB object sets or I may be interested in them. There are some updates or changes that have had to be made to certain objects over time, and maybe something Burke and I will talk about off of this call. But and this is just I'm intentionally kind of putting this up here as some of the potential struggles with development of some of these standards and benchmarking sets is availability, replicability, and making sure that things can be consistent as they are used across the research space. Particularly for an object set like this that relies on real-world objects, sometimes we have to deal with some of these potential changes and how to mitigate them over time. Moving further along in our complexity scale, we get to the NIST assembly task boards. So I believe there's going to be some more detail provided on these later, but we've also started featuring these for some of our replicated benchmarks that are available. And this year, the two kind of most notable events were a workshop that was held at RSS, where authors of accepted submissions that basically proposed work that they would do with the NIST ATB task board received one. And then there was also the IROS 2020 manipulation competition that used a variation on the task board, but basically two sets of those were distributed to different research institutions to use for the competition, just kind of further getting those task boards sent out there. And just as kind of a quick look for the current state of at least the first NIST assembly task board, there's been 29 of those kits distributed between the US, the UK, Germany, Italy, New Zealand, and Switzerland, and many more probably still to come. And then looking at the ones for the IROS competition, where because we were dealing with a remote competition where there are typically boards that are the kind of surprise the day you come to the competition, we had two sets, a practice board and a competition board that were distributed, and one was only opened on the day of the competition. But the point being that more of these task boards are starting to find their way into different research labs internationally. These ones into the US, China, Denmark, Germany, Japan, and New Zealand. So between this and the YCB object set, as well as some of the different NIST standard test methods that Joe was talking about earlier on, these are starting to get replicated and distributed for a lot broader use to many different research labs. And I think the hope with this group would be that as we start to further standardize some of the protocols or practices or metrics that use those artifacts, that we can then start to propagate them further and further, so that at least when we're all reporting results for one test method or one benchmark, that we all know we're at least using the same underlying protocol, underlying hardware, and what have you. Now, the last biggest effort that I want to just very briefly touch on is a project that is really focused on this kind of repeatable benchmarking concept. It is a collaborative effort between UMass Lowell and Oregon State University. And the goal is essentially to create a remote test bed that involves many of the kind of common benchmarking tools that we're all talking about here today, and making those available actually in a central location, but remotely accessible. So it's not just access to a standard set of benchmarks, but also a standard set of robot hardware that can be used to access those benchmarks. So this is just kind of a quick overview of some of the benchmarking tools that are going to be included as part of this system. But the idea would be that as a researcher, you would develop your code or parts of certain robot functionality, upload it to this system to have remote testing run at a later date, recorded in a standard format, and shared with the rest of the community, so that we can start to build up this kind of catalog of different robot capabilities and comparable benchmarking results across a variety of different tasks. For the moment, the tasks that are included in this test bed, which is still very much a work in progress, we've kind of split them into your more kind of basic grasping tasks and then more task-based manipulation. So along the top is the grasp reset mechanism from Oregon State University, which I'm going to talk about in a second. The shelf, which is based off of the ACRV picking benchmark, something that's essentially modeled after some of the Amazon Robotics Picking Challenge competitions, and then a variety of different objects that can be utilized within those test methods, including those from YCB and some other kind of canonical and sensorized objects. On the task side, there are designs from OSU that are going to be incorporated, such as the manipulation of door opening with all sorts of sensors spread throughout it, so we can get very high fidelity information about what occurred. A drawer, which is currently in that photo just missing the handle, but functioning very similarly to the door. And then the assembly task board. So we're trying to marry a lot of these efforts into this setup, as well as introducing some new benchmarking tools. Now, one that is probably a very interest to this group is this repeatable grasp testing setup. This is a device that has been under development from Oregon State University for a couple of years now, I believe, called the grasp reset mechanism. And you're not seeing a lot of the kind of inner workings underneath, but essentially the idea is to do very repeatable grasping from the same orientation, same position, etc. There's this mechanical setup that has no human involvement aside from maybe just the initial setting of the object, although there are some means that are under development for automating that portion. And you can do repeated grasp testing over and over. And you can see, I don't know if it's coming through in the video, but as this object gets reset, where it's kind of pulled back into the center, it is also rotated so that it can be grasped from the same orientation again. Now, the object being used here, of course, is a symmetrical cylinder. Maybe not the best demonstration of that feature, but you can imagine if this was another object, maybe say like a teapot where there's a handle on one side and you wanted to repeat that grasp over and over for some statistically significant results, this could help you do that. And we're planning on implementing this again from the remote settings so that people do not need to have all of this infrastructure set up at home before they can run this type of test. We're also looking at means to automatically evaluate each of these benchmarking tools. So for example, one tool under development is for the NIST Assembly Task Board, where we're using some computer vision techniques to automatically evaluate the end state of this task board, where the goal is either to assemble or disassemble it and the various tasks that are within it. Without going into too much detail of what that includes, it's a technique of taking out the background, looking at all the various kind of component states on that task board, and then doing some simple vision-based evaluation. And we're trying to improve this by adding additional camera angles and all sorts of things. But the main kind of thrust of this effort is to try to get a more standardized evaluation metric for each of these tasks that hopefully is not left up to human interpretation. Now, for all of those test methods, there's a lot of development that goes on through the years, from meetings like this, through workshops, through research, but eventually all of those test methods need to be validated. And what we commonly refer to this as is kind of round robin testing to exercise the different test methods. And what we mean by that is sharing, say, the instructions to build a certain test artifact with various different facilities, or sending a common artifact around. And what you're testing is a lot of different aspects of the test method itself. Is the fabrication of it repeatable? Do we get the same results by following the same instructions? Are the results of using the test method the same in different facilities when you're using the same robot? Or there may be certain robots that are only available at certain facilities, so you need to share them around in order to build up that set of data. There's also a lot of different contextual effects, such as the environment or other aspects that you may only get at one facility or another that could have some effect depending on what the test is. And through this exercise, what we start to do is gather up a range of test data that we can demonstrate the effectiveness and the robustness of each of those test methods, and then modifying the underlying apparatus or artifact as we need to. And this has been commonly used for other test method efforts, such as those for response robot evaluation, mobile robot evaluation, et cetera, and has proved very fruitful. So with all of those various test methods that I very, very briefly went over, the idea would be that we do this type of round robin testing where for some of them where they are intended to be, say, cheaply replicated and very easily usable, that we would either rely on others to make their own, and maybe we're reporting results in a common format, or we're sending them out to our robot armada at NERV and maybe putting it through its paces on a variety of different robot manipulators. There's a couple different ways that we can approach it. But what I wanted to mostly get across is that this is a really important aspect of this type of development, where we get out of the kind of planning and writing and actually get to physical validation and testing the data. My last little plug will be that if people are interested in the YCB object and model set or the NIST Assembly Task Board, those are both currently available for purchase through the NERV Center. And there's links right on our homepage at nerv.uml.edu. And I hope we can further spread some of these benchmarks into the rest of the community. Thank you.
Okay, this is Joe. Can everybody hear me?
Yes.
Okay. Um, okay, so thank you, Adam. That was very good. Um, Let me give the opportunity to any latecomers. I see Matt Mason joined us as well as some other folks to introduce themselves. Since I don't know exactly who it was, I'll just let you speak up and, just take turns, see how that works.
Hi, I'll go first because you mentioned my name. I'm Matt
Okay,
Mason, and that's it. I'm at Carnegie Mellon, except working from home.
okay, nice to see you, Matt.
Thanks.
Anybody else? Tapo?
Oh, hi. Can you hear me?
Yes.
Yeah. Hi, everybody. I'm Tapo. I'm a postdoc at University of Washington, and I'll be joining as an assistant professor in Cornell University in summer 2021. I'm happy to be here. And sorry for the earlier message I sent to everyone by mistake. Thanks.
No problem. Thank you. Kayu? Hang? Or maybe I'm an official name hacker here. Uh, Xiaowei? John, would you like to introduce yourself? Okay. Anyone else? All right. So speak up later if you having problems with your audio. Anyway, so the next point of our discussion, Adam, can you stop sharing? Make all right. And hang on one sec, guys. So the next topic of discussion is a discussion. So before we move on to talk about other ideas, let's have a discussion on what we've talked about so far in these grasping end effector type of test methods. Trying to figure out the best way to proceed. Oh, wow. Sorry, guys. Um, Here we go. Okay. So we need to proceed. So, first of all, ongoing, as far as this group exists, there's always the opportunity to suggest additional performance measures and test methods. So, if you think them up as maybe as your efforts in helping us work through the current existing test methods, feel free to propose new ideas. But I would suggest that maybe we start the effort by choosing three existing performance measures. Maybe some of the ones I presented at the beginning, some of the simpler ones like grasp strength, finger strength, things like that. Um, and to start out with, for each of those, we can review suggested revisions to date from our past RHGM feedback. So NIST will do that effort in documenting all the feedback and presenting it to the group, um, and trying to formulate improvements to the test methods as we document them as an IEEE standard. And we will include also any implementations in papers of these test methods that reference NIST work. Like I said, there's about 50 references to the work so far. And we could do a more detailed literature search to see if we could find anything else. So those are my suggestions, but I'm opening the floor for anyone who would like to discuss what to do, even step up and say, hey, I'm interested in spearheading, helping to write one of these test methods. because I'm working on this in my lab, or I have some ideas to improve it, and I'd like to do an implementation in my lab, things like that. Um, or it could be one that's you know, say in-hand manipulation if your research work is focused on something like that, or even in-hand manipulation based on gating. You can step up to something like that and start working on it, even though the group is not focused on that at the moment. So there's lots of avenues we can go down, but we do need your help. So is NIST, you know, it's we don't want to do all this work ourselves, not because we don't want to do the work, but we don't want to be the writer of the standard. This is a group effort. We need everybody's input into the effort. So with that, anybody have any comments they'd like to share?
Real quick, Joe, when you share your screen, we see gray boxes.
Oh, really? I'm sorry.
Yeah, there's,
Oh,
I guess, a window that, yeah.
Is that better? Yeah, I
That's
didn't
better.
hit okay, whatever that was. Sorry. So yeah, those are the 3 discussion topics I just mentioned. But in any case, yeah, I don't know how to start. I could start by just saying these are the ones we're going to tackle. Anyone want to volunteer? But I'd like to hear some input from people.
Yeah.
Go ahead, Sun.
Yeah, so I tried to really search for the raise my hand button, but I couldn't find one. So I just raised my hand.
Anyway.
Yeah, so I heard a lot of very interesting ideas in the presentation, particularly one kind of related to what I'm participating now is this remote evaluation effort. So I think there are actually another one in Europe as well. And I think there's also another one in Australia. But because of COVID, I think you know, a lot of us could not go back to lab, and also some of the researchers in computer vision doesn't really have the platform to do evaluation, and they are familiar with you know, they have this evaluation in their blood because you know, you have to have a standard evaluation when you submit a computer vision paper. So providing a platform, a standard remote platform, I think is quite important at this time. So I just want to introduce one we have developed it for the latest competition. It is called Open Cloud Robot Table Organization Challenge. So the challenge basically is ongoing. It's supposed to be part of the IRAS because the delay. So the competition will be finished in a week also. So for this competition, we provide a physical platform with several UR5, UR5E, I think, robots. And standard tasks also were designed based on WebCP objects. So the task was to arrange a number of objects on a table from a certain layout to another certain layout. But I think this can be generalized, and I really was interested in seeing more of this, and very excited when I saw the effort from the UMass and I think it's OSU, right? So by doing that, I think it provided a lot of support for the community, especially for the people who cannot get access to the robot or doesn't have a robot. Yeah, that's my take.
Yeah, so my feedback on that is um, sounds like maybe Adam could possibly help in that area with his nerve center's work. We can certainly lend out certain measurement tools like maybe a split cylinder artifact or two, depending on the size. Yes, Lyle, just a second. And as far as robots and hands, in particular reference to this work we're talking about right now, I suppose if someone's developing a hand, they could possibly ship it to Adam to do some testing. Adam, you could tell me to shut up anytime you want, as a means of performing the tests. But go ahead, Adam. You got any?
No, I was going to say
Yeah.
this all sounds like a good idea. I'm more I think we should chat maybe offline more in detail. I'm curious how your competition is functioning with this in terms of how people provide code and that type of thing, because we're spending a significant amount of time doing that. But
yeah, certainly. So we do have some software engineer developing the system. Basically, the participants can just submit their Docker image of their solution, and we have automated way of tracking, evaluate their solutions.
Gotcha. Yeah, and then Joe,
so
for
we
your
should
other,
talk.
Yeah, and then Joe, for your other comment about sending hardware around, I think the idea of further providing the test artifacts themselves, or maybe trading them around, is I like that idea a lot. And certainly, if we have a good way to send hardware under some specifications to be tested, say at Nerve or elsewhere, we'd be interested in that as well. I know for the moment we're probably not set up for that, but it's something we could work towards.
Right. Because you're suffering from COVID, the COVID blues also, right?
Everyone, yeah.
Let me give Lyle the opportunity. I think he raised his hand.
Yeah, I did. I just sent you a note in chat. Yeah, as to which of these to focus on, one of the things I'd be curious to hear from you, just with your NIST hat on, is what do you want a good benchmark to be? Is this, in other words, are you trying to distill sort of experimentally transferable properties of grippers directly? I can tell you that, so we do a lot of customer evaluation. What customers will do is they will want to put your robot in front of their top 100 fastest movers, and they will want to know what you can manipulate and what you damage and how fast.
Right.
Which is an extreme, and that's probably on the other extreme end of being very difficult to scale, even between customers or within the same customer in a different workflow. So I don't know, from that end over here, we have all the way down to this question of, are we measuring how much force something exerts, or specifically characterizing force sensors or things like that? Just from your perspective, what's the best place to start?
Right. So there's a couple of types of testing. We categorize it as elemental and functional. Sounds like what you're talking about is more functional testing. And most, to be honest with you, most of the grasping and manipulation work that's being done, including the NIST task boards, is functional testing of a system. So these elemental grasping, end effector type tests are looking to quantify the particular characteristics of a gripping end effector. So what we're looking for there is a set of tests that are repeatable across the community with a good statistical significance in the data that's collected, so that you can report your findings in a uniform way, right? I'm not sure if that answers your question, or maybe someone else can help with this.
I wanted to maybe kind of bounce off of what Lael was saying earlier about some of these tasks, at least maybe in what Joe, maybe what you were talking about at the beginning, seemed more like evaluating primarily the hardware capabilities of the actuator. And some of the other tasks, including some that, for example, Adam spoke about, seemed like they were more at the end of the spectrum where perhaps software abilities, controllers, your sensors, your ability to integrate the information, sort of the entire control loop would matter more than the specifics of the hardware. And so, it's kind of a confounded measurement of all of that in the loop, right?
Yeah.
These sets of metrics, these kinds of measurements will be of interest to many different, to very different kinds of communities of researchers and practitioners, right? So there are hardware developers, and then there are people interested in reinforcement learning and people interested in developing better controllers. And so the challenge in trying to come up with a metric that is of relevance to all of these different communities is just that fact that there's hardware and software together determine the eventual performance, right?
Yeah. Well, I think when it comes to the initial presentation I gave on the different characteristics of a robotic hand, I think there's a little bit of both in there, right? So there's some really raw traits like the capabilities of a finger, applying a force to an object or a grasp force. Those are pretty rudimentary. But when you're talking about, testing a system's ability to detect slip and then feedback through the control system of the hand and adjust the grasp force, that's more of a system level test, but still it's confined to the hand, or excuse me, I should say end effector in this case. So you should know that all the test methods that I went through for this first standard effort you could do with a hand by itself. You don't need, although you could use a robot manipulator to do some of the tests, you don't need it.
Right. I think, yeah, sorry, go ahead.
I was just going to say, adding on top of that, I think a lot of these tests, and at least the way that I've seen them done in other robotic domains, is they're usually very holistic in that you may have whatever your perception setup is, however your software is running, yada, yada, yada. But at the end of the day, the metrics, say, aside from those that are kind of the elemental hardware ones, are very task-based because, say, kind of going back to, maybe to Lyle's point about, what the consumer might care about is the measurements they can use to calculate their productivity. Is it going to match their solution, whatever that is? And I think what's nice about that too is that it means that not that we don't have to care about all those different elements coming together. We obviously need to be cognizant of them and probably want to capture what those are in some way that makes, characterizes it correctly. But if we focus more on what are the task related measures that they can use, then we can be a little more agnostic about it. I just posted a paper I think it's from a few years ago now, but it's a very basic editorial that Berkeley guy, whose name I can't remember right now, had put together, Ken Goldberg, that was just about a universal picking metric. It's really, really basic, and we can add some more, complexity to it as we need to. But I think those types of measures are probably the types of things that would probably have the most impact and be easiest for us to start with.
So I like the idea of having these simple task-based metrics. I wasn't really suggesting that one of them is better than the other. I think the way that I think about this is that if you are measuring performance on specific tasks, they're obviously closer to eventual end applications that a consumer might care about. But on the other hand, those metrics are now specialized to that specific task, right? Whereas when you're measuring something like hardware capacity, the advantage of that is that hopefully that transfers to performance across a wide range of downstream applications. And so one way to think about this is that if we are measuring some hardware capabilities like the ability to exert force, the ability to repeat your motions, etc., how well are we able to quantify the extent to which those metrics predict performance on a wide range of downstream tasks for the best controller, right? For the best possible control system that you could set up with, can we now measure some kind of correlation between these hardware capabilities that we measured first and the eventual task performance across let's say, a set of 10 tasks that are representative of the potential applications of the end effector.
Right, right. Yeah. So the way we envisioned, so when we first started these end effector performance measures, was more in line with you buy in a robot manipulator, and they'll come with specification. What's the work volume? What's the repeatability, etc. It's more along those lines. It's a standalone piece of hardware that you're buying. It might have sensors. A lot of robots now have internal force sensing, etc. But you're looking at the robotic hand as the system. Now, when you're getting into more of the application space, then you want to test the system. And so it might be that you home in on a set of robotic end effectors that could meet your needs, but then you're going to have to take those based on those specifications I talked about. But then you're going to have to take those hands and bring them to your application domain and really do some significant testing to figure out what's going to best work for your application space. And with that, I should reiterate that, like we had a discussion before a lot of people joined today. What we'd like to do is turn this group of people into a standards working group that not only is addressing this one particular end effector set of characteristic performance measures, but as a group that produces several different standards, some of them being more towards the application space. This is just the starting standard that we're trying to address because we formulated a lot of work in the past, and we think it's time to start trying to put something together. And it's not to say we can't do things in parallel either, but I think that the group as a whole can tackle both these elemental type performance measures that define the characteristics of a piece of hardware, as well as more so the application space, such as the NIST task boards, the YCB object set, and test methods around those, etc. So try to think big picture. What I presented earlier today is just a small snapshot of the first standards effort, and then there'll be many more to follow, hopefully. And that's what our next discussion is. Bert Colley is going to talk about some of the work that he's done with the YCB benchmarks and some of the test methods they've been developing. Likewise, Kenny's going to talk about the NIST task boards and talk more about performance measures for task-based operations of systems.
If I may add something. So actually, I'm impressed by the big job that you already did. What has been puzzling me for a long time, and I think is one of the bottleneck in developing benchmarks for real robots. Now, I connected to a comment that was fun, because it's how we scale from this simplified testing environment to the real world, where, for example, dimension can change, object position can change. And this, I think, opens two issues. One is randomization with related statistical measures, and the other is the link with simulation. Because if you have enough randomization, probably to repeat thousands of times the same test with changing positions or lighting or things like that could be very, very heavy. I mean, this is, if you wish, further steps. Those are further steps, but I'm curious what you think about that.
Yeah. So you're asking me how to go from these elemental to more integrated tests. Is that your question?
Yes, because it's difficult to understand how this has to be done. And
right.
Thank you. But it's difficult to understand how you can scale from the toys situation that you have built for performing the benchmark to a real world situation. So how I can know that my grasping system will work in my factory or my hospital, whatever.
Yeah, I don't think you could determine that until, like I said, I think the way we envisioned it originally was you could use these performance tests to develop the characteristics of a robotic hand, for instance. And you could use that information to possibly pick, envision a bunch of tactile, robotic hands with tactile sensors integrated. We're not there yet, but eventually there'll be a lot of products on the market. So how do I know? How do I pick from 100 products out there? How do I pick maybe 5 products to introduce into my factory test domain to see what's best for a particular application? So once I use these specifications that were developed from these tests, I can say, okay, I'm gonna purchase 5 different robotic hands. And I'm going to bring them into my research lab in my factory, and I'm going to try to implement some of these more functional tests. Maybe it's a service robot task, and there's a YCB object set involved, and they'll follow some of those functional tests. Or maybe it's an assembly type task, and they'll use maybe a NIST task board. Eventually, they'll use the actual product that they're going to assemble or warehouse and things like that. But I think it's a multiple step process, and these elemental methods for end effectors is just a way of specifying their capabilities so that you can figure out which, a small subset that might fit your application space. And then you got to move on and do a lot more testing. Yeah. Because that's just my vision. I'm not sure.
Thanks.
Someone else raised their hand. Who was that? Speak up. Yeah. Was it Lionel?
Yeah, it was me, Joe. I'm sorry. I just would like to get back to the previous discussion with Dinesh. I would be very surprised if these low-level metrics do not correlate with high-level performance. Well, it remains to be seen, but I like the fact that you are starting with low-level, really hardware measurements. And I can give you an example. Very recently, we published a paper with Xiaowei, where we used the FinRay effect finger from Festo, a soft finger, and we did some measurement with that, and we put them on a gripper which creates 200 Newton of grasp force, and the output we had like 20. So the FinRay effect fingers are actually not very good. You cannot really grasp securely many objects. So, of course, you can try to compensate this with control systems and advanced sensing, but there are physical limits to what you can do. At the very lowest level, this is a hardware issue. You cannot do more than what the mechatronic system is allowing you to do. So I actually like very much that you start by measuring that. Of course, then the control system is also, and the grasp planning, they're all essential pieces for the industry, for applications. But low-level hardware issues are important too. And the second point I want to mention is that you specifically requested some help with measuring with the grasp efficiency test you're proposing. I would like to help you with that. Because first, I believe we already have all the equipment and apparatus to do that. We have the split cylinder artifacts, we have the linear stage with the sensor. We have it already. So it's basically, it will require minimal efforts from us to help you with that. And probably you're not aware of that, but we published a paper also, I think it was like 15 years ago. It was a very long time ago at ICRA, where we do something, it's not exactly the same, but very similar. We measure slippage with our 3-finger robotic hands. And when we detected the slippage, we bump up the actuation force to stop it from continuing. So it was kind of, I did that when I was a PhD student, you know,
Okay, good.
15 years ago. So I'm interested, I can help you.
Yeah, that's
with,
great. Yeah.
Yeah,
Yep.
that's my.
Yeah. No, I don't, not sure if I saw that paper, but yeah, I have to say that most of the efforts that we've been involved in here were drawn off of research papers that did measures to measure the performance of their research. And yeah, we're just trying to formalize everything here in a community-driven fashion so that everyone agrees on how things can be measured. And it just makes, if you get consensus, then it just makes them, I think, more widely usable by everyone. People will want to use them. So that's important. And it's important that they're documented well so that people can implement them the same and compare results. All right, thanks,
You
Ryan.
see me, Joe?
Yes.
Yeah, I might have one input. So I find the test you presented very interesting. I think it's kind of a test we were doing internally at Robotic to try to characterize the hand. There's maybe one thing it's that I see that you will not be able to capture with those tests. So it's probably one of the main failure we see in the field with the robotic gripper. So as you probably know, robotics, like some other gripper, use a self-locking transmission to maintain forces. So in your force test, you probably see that things where when we apply forces, we apply that level of forces, and usually the transmission keeps something like 80% of that force. And then it's locked in the mechanism. And one of the failure we see is with convex object, when we have high inertia forces on the object, or when we start to apply forces on the object. And I think as robots move toward assembly task, I think it's something we see more and more. The fact that we use self-locking transmission, if you have a very tiny, infinitesimal movement, depending on the shape of the object, you can basically lose all the grasping forces. So for us, it's one thing we see in the field, and it's something we work on. We use different transmission, we use brake, but definitely it's one big issue for us. And I'm not sure with all the tests you presented, we would record that things.
Yeah. Well, that's good. Yeah. So yeah, we haven't developed any of these with those types of gripping systems in mind, simply because we didn't use them. So it's good to have you as part of this team so that you could possibly help us add that functionality into the tests. Yeah. Yeah, our preliminary work was strictly focused on, 3 or more fingered robotic hands, typically exhibiting force control capabilities. Yeah. Excellent. Thanks, Vincent.
Yeah, thanks.
So you think you can get involved and try to help us address some of those problems with our measures?
Yeah, definitely. It's something maybe we should have like a relation between an infinitesimal change of object circumference, or I don't know, object shape, in relation to how much you lose forces quickly.
Okay.
I think, but I can see that test being quite challenging. But definitely, yeah. What if we change bit grasping position? How much force do we lose?
Okay. Excellent. Okay. So any other
Is there
comments?
is there anything among the current suite of metrics for that measures the ability to modulate sort of the impedance of your fingers? Because this is pretty important in many contact-rich tasks, and it would be good to have. I think it would be something that would be predictive of downstream performance.
Right. So yeah, I guess I guess nothing to measure that directly. Yeah, but it's something to consider for sure. Yeah.
Even beyond modulating, just characterizing the stiffness of the fingers is probably a relevant metric for a lot of tasks.
Agreed. Agreed. Yeah.
Okay. So these are great ideas for more performance measures for sure. This is what we're looking for. So yeah. So I guess what time is it? Let's see. Okay, it's almost coming up on 11 o'clock. Would anybody like to take a break? I didn't really incorporate a break into this meeting, but if you would, feel free to do so now. We can continue this discussion, or we can move on to the next presentation, um, diving into some of the futuristic work we can address, more geared towards functional testing. Um, I guess I think we just need to keep a mail list going, present some new ideas. We'll document them here. You can, when we have our regularly, try to have some regularly scheduled meetings to address some of the work that we're doing. And at that time, you could bring up some additional ideas. We'll document them. We'll assign people to work out the details and things of that sort, to add these performance measures to the end effector type performance measures. So I guess probably the best thing for us to do now is take a quick break, and then come back and listen to Burke and Kenny talk about some of our uh, functional type tests that we've been working on, and try to plan for the future of some other tests. Some other standards that can evolve from this effort.
When do we come back, Joe?
What's that?
When do we come back?
We come back. Let's just do. I got 10:45 exactly, so let's just do 10 minutes. So we'll start at 5 of.
Sure.
Okay. Thank you. And you can keep talking if you want. Help yourself. Have a conversation with your friends.
Joe, I just wanted to say I unfortunately have to leave to join a defense committee, but I'll catch up on the rest of the meeting afterwards. Thanks for arranging this. This has been great.
Okay, Dinesh, thanks for joining us. Much appreciated.
Bye.
Bye.
Are we on? We're on break time right now.
We're on break.
All right. How you been, Joe?
I'm doing fine.
Yeah.
So you were the culprit that canceled my
it's my software. I've got to figure out what's going on there.
I swear you did that before too.
I know. I don't know what's going on with that. I've got to figure it out. I've got too many things and affiliations I'm managing. So I'm leaving SynTouch. I'm still affiliated, so I was moving it over to a different calendar.
Yeah, no problem.
Yeah. Sorry about that.
I just want to make sure no one got the wrong impression. If anyone else even saw it, I have no idea.
Yeah, I
didn't even notice it till today.
Yeah, I made a copy and moved it over to a different calendar, and I'm assuming that was what happened. Too many affiliations to manage over here. But anyways, if you wanted to update my address, I'll give you my new email. So I'm going to be phasing out of SynTouch stuff.
Okay, that'd be great.
Yep.
So Lionel, you think maybe you could come up with a bit of a scope for running those tests that you mentioned for grasp efficiency. Maybe take a look at what we have documented to date and give us your feedback on it. And
Yeah, I already did. I think the main point now is for me to get back to the lab and try it actually with some of our prototypes and grippers. I must say that due to this whole COVID situation, getting back to the lab is easier said than done.
all right.
So I cannot give you a clear calendar about when this could be done. But I'll keep you posted about that. And if anybody else wants to join in, just let me know.
Yeah, great. Great. Thank you. Okay, folks, this is Joe. I guess we should get going again. Burke, are you there?
I am here. Just a minute, though. I will grab some
Yeah,
water. Thank you.
That's fine. That's fine.
Okay, I can start anytime.
Okay.
All right. So hello again, everyone. I just want to very briefly talk about some of the benchmarking efforts that we have done, mostly within the context of YCB set, but also it was really a collaboration with many, many people. We basically, basically the timeline of how the YCB project started and like how it progressed throughout the years. You can see here. I just want to very briefly talk about this process and just want to propose a couple things about how we can move further, and really want to at times emphasize what things worked throughout the process, what things did not work, and what we could do better, etc. So most of our efforts can be grouped into three main categories, which is like creating benchmarking tools, connecting researchers and creating common venues. And I believe these are all very connected and mostly towards creating a community for benchmarking purposes, which I believe is very, very important. And again, just like Joe was saying, this needs to be a community effort. Otherwise, people, for example, individually proposing benchmarks can go up until a level. And most of the work that has been done are really valuable. And for their impact to be much more than it is currently now, I think like this group or within IEEE or NIST, we can definitely boost the impact of the current work as well as some future work. So the benchmarking YC benchmarking project launched in 2014, where we basically put together some objects together, as many of you know. So the problem that we saw was there are so many different objects that people were using that were randomly chosen for the experiments, and what we wanted to do is to create a common test set with the initial group that you have seen here, and we also created high quality models of these sets. Then the YCB benchmarking group actually grew quite a bit after that, especially UMass Lowell took over the distribution of the set and currently maintaining it very strictly and systematically, which is awesome, which was very important for the future of the project. Google came in to provide higher quality, perhaps object models, so that the model side of the YCB object and model set became a little bit more stronger. So essentially, we came up with the set and high quality 3D models. And we presented this set in 2015 and in an ICRO workshop, and we distributed these sets to the attendees for free. So basically, we really transported these sets, gave it to them on the spot for free, which was, I think, very important to for the dissemination in the first place. What I feel like is benchmarking efforts is relying on two main things. One is making it very, very, very easy for people who are using them, making them very available. And the other is that we need some leaders of some specific groups to be on board. Because once these objects are start appearing in prominent groups within some subdomains of manipulation, for example, in this case, it became much more easier for people to adapt them, and its visibility became very pronounced. It was the set was very much out there after this 2015. The problem was that though people were using these sets, but kind of still in a random fashion. So people were basically choosing the set, some objects from the set, conducting these experiments within those like subset that they decided. And but there were no experimental procedures. There were no standards. There are no metrics to quantify the performance of the systems. So in a way, the set answered a very limited part of the benchmarking problem in that in that time, which was the repeatability of the sets of the experiments. So basically, once someone propose an algorithm and provide some experimental results, another group could use the same object set, the same objects, and then replicate the experiments, which was a good step, but without experimental procedures clearly defined or quantification metric set, it really did not have a lot of value, to be honest. So what we then do is we try to connect the researchers together and try to come up with these experimental procedures. And that happened in 2017 IROS workshop. So before the workshop, we actually got in touch with many people in the field, asking them whether they want to create these procedures. Again, us creating procedures ourselves doesn't mean anything. Pretty much the community should be on board. So what we try to do here is to form some work groups that are made up of communities, research labs from all around the world. And so what is important, for example, you see here three of the work groups that we have created, that we have formed, and the researchers are from different universities, different research labs. So this helps basically a couple things. One, people cannot design these benchmarks according to their systems, right? The benchmarks should be valid for at least 2, 3, 4 systems. Plus, the groups themselves here, for example, if the force sensing and manipulation group, there are like 5 universities here. Even if they only them apply this benchmark, we already have 5 different results to compare against. And from that point on, the idea was that from that point on, other people will also be on board for proposing, for utilizing these sets and compare the performance of their system or algorithm with the presented results. And just as I said, we try to foster collaboration between people, and this happened like 2-3 months before the workshop, and people worked on these benchmarks and presented their results in the ICRA, in the IROS workshop in 2017. And we organized another, the IROS 2007, in IROS 2017, we basically, they proposed the benchmarks that they came up with, and they received feedback from community, and they then improved their benchmarks a little bit. But then comes the next problem, which was the rewards for producing these benchmarks, which was how can we create some common values that basically can result in some dissemination of this work, but also it becomes a publication reward for people who are participating. For that, we organized a special issue in RA letters. Some of the work that has been presented previously in this session actually had papers in this special issue. Joe had some. I know Maximo has. Adam's group has a benchmark in the special issue, etc. So that reward mechanism was pretty much needed for have the things get going, because that also gives a concrete goal to the researchers. This is also important because basically we work with goals and deadlines in the research community oftentimes. Without deadlines, we just can continuously improve these mechanisms, but these benchmarks, but it then does not have a concrete result necessarily. So while organizing the special issue, we asked the people who are interested to submit some letter of intents, and we received like around 25 letter of intents. And among these, what we have done was we looked at these 25 letters, and some of them were proposing benchmarks for similar applications. For example, cloth manipulation. Cloth manipulation is not a very big domain, like it's not as big as robotic grasping, for example. So it may not make sense to have multiple benchmarks in the first place when it comes to cloth manipulation. So we actually connected people that are trying to propose the same benchmark together. some of these letters were coming from the work groups that we have worked together in IROS 2017. And we gave them detailed feedback about what they are proposing, some guidelines, both for authors and reviewers of these submissions. And we had yet another workshop in ICRA 2019 that now these groups that sent us the letter of intent presented their ideas again to get feedback from the community. So we really try to close the loop whenever possible. After they received these feedback, they updated their benchmarks before submission. And finally, the special issue has been published in 2020, January. And now we have like around 10 benchmarks that are available in the YCB benchmarks website for various subdomains of robotic manipulation, which is like, for example, bimanual manipulation, for pick and placing, for grasping, etc. And here are some future steps, and they actually, I think, boil down to a couple main points, and would be very happy to discuss any of these. So this is, again, not specific to benchmarking grasping mechanisms. It is perhaps a more, some suggestions about more broad benchmarking for robotics, but basically identifying the subcategories that people would be particularly interested in would be a good first step, I think. And then and identify all the benchmarks that are out there for robotic manipulation. And we can go retrospectively, so we can actually have a really exhaustive search about all the benchmarks there is, and having an updated website, a website that updates frequently, that presents all these benchmarks to the community, and basically some list of groups who are using them, leaderboards that score high for these benchmarks, etc. And here, I think what is really important is working together with NIST and working together with IEEE, specifically with the Committee of Performance Standards and Benchmarking. I guess Fabio is the head of that group right now, because basically when we try to say, when we ask people, please send us your benchmarks, let us put them to our YCB website, so that it will be like, okay, you use YCB objects, here are your benchmarks, here is a leaderboard, etc. There were, again, a couple problems with that. One is it takes a lot of effort to centralize everything, and we really didn't have a lot of time to spend on it. So definitely we should reserve some effort to do that. But second, perhaps more importantly, I mean, people didn't see a particular reason to use YCB website as the main portal. If we are doing this with NIST, if we are doing this with IEEE, and especially with the Standards and Benchmarking Committee within IEEE, that will give it a legitimization to have a central portal for these efforts. And basically, it's creating something very similar to what a computer vision community has, that we basically, anyone who is working on these particular problems, one of the frequent and common things to do would be to go to that website and check what benchmarks are there, who scored better, in some of these benchmarks, etc. So it really boils down to creating a very active community, which actually we tried with the YCB object set, but it was not as successful for the reasons that I was talking about. And also, I think it's very important to understand what is working and what is not working with the current benchmarks. So we should go out there and make surveys for groups who utilize these benchmarks. What was their experience? People who did not utilize these benchmarks. So basically to be a little bit, let's say, provocative here, like why wouldn't people not be using these benchmarks much more commonly? For example, when they design a hand, why did they just don't go for the, let's say, NIST benchmarks or any other benchmarks that I was talking about before in the first place? What is that reason? So I think there are there could be different reasons. One, some people are against the idea of benchmarks and performance quantification for many different reasons, and some of which are actually valid reasons. We have received those kind of feedbacks a lot throughout our process. But I believe getting ideas from them are also very, very important. So we definitely need kind of quote unquote devil's advocates in this process. And but there are also some practical reasons that people would want to utilize these benchmarks, but one reason or another they are not doing it. So in the workshops that we have organized, when we asked to the community, to the audience, which were like around 30, 40 people oftentimes, but if there would be benchmarks for your particular domain, would you use it? And they always say yes. But so what is stopping them? I think it's very important to identify that. And last but definitely not the least, if we can maybe come up with a portal, a very active portal that we update very frequently, we can announce this, perhaps with a short paper, maybe in Robotics and Automation magazine, to understand whether these, to announce and make people know about what is going on and disseminate the effort. So yeah, these are some collaborators that we worked with for these workshops or these benchmarking efforts throughout the year. But yeah, this is pretty much what I want to talk about. Thank you. So happy to discuss anything here. I guess I received, so there was a chat that I couldn't read in the first place. Yeah, the chat, so Jeremy was saying people won't use benchmarks and metrics if they don't find them useful. Sure, and again, some people are categorically against benchmarks and metrics, but also there could be some practical reasons that, for example, they might not have the instruments that that would allow them to replicate the NIST's benchmarks, for example. That could be it could be a practical reason. So there is an activation energy, I feel like, that we should address and it is very significant. It requires a lot of organization and effort, I feel like.
Yeah, I think everything you're saying, Burke, is based on just making them more accessible. And once they become accessible, more people will start to use them, and then they'll become popular. And once they're popular, then more people would be inclined to use them. And I think some of the stuff we're doing with Adam Norton in making our measurements in protocols more accessible through those guys, because we're not set up to do that kind of stuff. We just work out of a lab and we come up with ideas, and Adam's helping us to get these out there, and I think that's making things more popular.
Yeah, and also, so for example, Lyle posted a comment here saying, just rather a cynical view, half of being a successful research publisher is carefully choosing the metrics, and perhaps they were choosing their objects accordingly, right? People were choosing the objects that make their algorithms work much better, indeed. So, and over there, what we were trying to do is to make multiple research groups work together so that they do not overfit to a particular algorithm. So they are perhaps working on different, let's say, graph planning algorithms. Completely different platforms didn't work together before at all. And then when they start working together, hopefully some of them will try to pull it to their direction. The other ones will try to pull it to the other direction, and we get a benchmark somewhere in between. And that's, I feel like, more or less what has happened in the publications on the array letters.
I think that's a good point, though. You have to really think about who the end user is of these metrics and measures, and that's going to dictate how they evolve. If the end users are academic trying to benchmark their technologies, they're going to converge to like toy cases where it's just, this makes my technology or algorithm work well. And I think the goal should be to really converge towards actual use cases that will be used. Like utilization is really the ultimate metric. Are people actually using the technology? Not is it performing well against some metric? So we have to really think about use cases far more than toy cases that might highlight a particular technology.
I'll add a certain mea culpa. When you move to industry, this pressure or sort of conflict of interest doesn't disappear, because you want to do the same thing with your customers. You want them to evaluate you by a metric that's flattering to you. And we have a marketing department, and that's their job, is to try to come up with metrics that are flattering to us. Even when we have, I think part of the challenge I see is just that there has to be a reward to adhering to the standard. There has to be some, because it's, people are going to have good arguments as to why your metric doesn't measure what they're really doing. And we have that complaint with every customer whose products we test against or whose workflows we test against. We can always point to something they could do that would paint us in a better light. But the value is that if they choose one thing and evaluate everybody, then there's a common standard that, that gives you some comfort in comparison. But yeah, I think that part of the challenge I don't know. There probably have been papers written on standards like ImageNet or something like that as to why they succeed, why people year after year write papers that are targeting the same test. I don't know if there's a good meta study on maybe trying to measure for how many years any particular test or score seems to occupy the research community. Is it a good run if you have a metric that lasts 10 years? It depends. It entirely depends. I don't know. So to some degree, that's probably a lens to look at it through.
So maybe the question. Oh, sorry.
May I say what I think in the chat? Actually, Lyle was saying that he was suggesting a cynical view. I think that the real roadblock or at least damper of the adoption of benchmarking in the community is that if you don't enforce reproducibility of results, it's much easier to score sites by saying something sensational, even if it is not tested. Because, and I'm afraid that the whole community is kind of poisoned by this approach. So what we are trying to do in the Robotics and Automation magazine is a gentle nudge to push people to publish reproducible articles, because in principle, a reproducible article should be a result that everybody should include the results that everybody can check. So what I was thinking now, I just thinking aloud with you, if we shouldn't add to the list of characteristics required for a reproducible paper, at least to suggest that it refers to some existing benchmark. I think we should do this further step. It's true that we have very few reproducible articles. Actually, we only have a magazine where you can submit a reproducible article. But I think that if you don't nudge the community in that direction, there is not a real benefit to benchmark your results. Well, there is, if you are a real researcher. But in terms of impact, if by time we don't push people to publish solid, reproducible, and measurable results, the community will continue to be cautious, no? Because that's my point. So we can think about that, at least to do something like what we are doing with CodeOcean and IEEE data part, no? Because right now we say, if you want that your paper is considered as a reproducible article, you should allow us to assess your code, your data sets, and even the hardware identifier. Further step could be, if it is about grasping, you should refer to some existing. So it is recommended. It's a good point for being accepted that you refer to a benchmark. For example, what you are proposing. But for sure it's not perfect. For sure it will require a learning process to be refined over time. But I mean, you have to start somewhere. So I'm just sharing this idea with you now. But probably is a further step that we may do. So it is about grasping. There are already some benchmarks for that. It is appreciated that you refer to them. This could be. Because we think that the community is not ready to say only reproducible articles and benchmark and the paper will be accepted. This probably is too much. but at least we may start to push, hoping that the good work over time prevails with respect to bad, so less structured work prevail. So it's like thinking that good stuff will in the end win, but we don't know, but we hope that, right?
Yeah, and I feel like, for example, the conference publications are a lot more hectic, right? Like there's a strict deadline, and like everyone is working towards deadline, and like experiments are done in the last week, if not days, and like, you know, put together quickly. Like this is not a very uncommon scenario for, especially for conference publications, but perhaps the journals can put higher standards in terms of, indeed, like, I mean, more journals perhaps like can put higher standards in terms of reproducibility or adapting benchmark. Like when it comes
within the board of the magazine, but I think we may at least add again in the form of if it is a paper about grasping and manipulation, you know, there are these standards, maybe benchmarked standards, so maybe it's good if you refer to them, not as a mandatory thing, but at least if you don't want to use that, please use another one, propose another one, and motivate the proposal, because I think it will need some time to. But if you don't start somehow to nudge in that direction, it's unlikely that something, because it's too easy to show, look, my robot fly. I don't want to give an example, no, but you may put two ends on a rocket. That would be tremendous results, right?
Yeah, and also
not aerial, rocket manipulation.
I feel like a common venue for like that we can have all the benchmarks that are available, etc., could be very useful. For example, in the case that you were saying, because then reviewers can point to that, right? It will be easier for reviewers to point to that. It will be easier for journals to tell reviewers to point to that, for example, or the editors of the journal, etc. But again, I feel like as the one of the last things that I want to say. Oh, by the way, the computer vision community, indeed, their benchmarks change every year because they actually succeed their benchmarks. I don't know if that would be feasible for robotics, but I mean, even if we, for example, update the benchmarks in every 2 years or something, if there's a mechanism to do that, that would be great. But like one last thing that I want to say is, if there's also there are very significant pitfalls for using benchmarks. Again, that's why I feel like we need some devil's advocates on board, because people do have serious concerns about using benchmarks, and if it is enforced with more and more venues, I believe some people will have significant objections towards that, and I think we should hear those objections and try to address some of them as much as we can. And yeah, that's the last thing that I want to say.
So I think we're moving in the right direction in making these benchmarks more accessible to everyone, and like Fabio suggested, in soliciting research papers to not so much demand, but highly suggest the use of benchmarks to report your results of your research. You know, when it comes, I work a lot in industrial robot safety standards. So these standards they're not enforced. They're industry consensus standards. In the US, OSHA doesn't require them. But if you hurt someone with a robot and you weren't using them, you're probably going to get in trouble. so people over the years have learned to adopt these standards, because of their accessibility and their popularity. Everyone else is doing it, so we're going to do it. So the more we can go down that road, the more in our short span of 10, 15 years, we might see something good happen out of this, where everyone is reporting their results using these benchmarks under IEEE's standards portal. Yeah? And one, I think, Elaine, that was probably you, maybe, talked about trying to bring in, yeah. So she mentioned that. Oh, are you there, Elena? Okay.
Sorry,
Anyway,
I was muted. Yeah.
okay.
Yeah. So you want me to just, yeah. So what I wanted to point out was that the constituency that's represented here is reflective of where the state of this new technology is, which is it's still pretty much in the research world. So I would say that without exception, everybody who is in this meeting produces, some aspect of the technology. So for a standards body, at least in the United States that's ANSI certified, you have to have a balance between the different constituencies, and that has to include the end users. Those tend to be more difficult to get to participate in standards committees across the board. But I think that if you get somebody who is interested in procuring these systems or investing potentially in further advancement of them, that can be an enticement for people to, honor the benchmarks. But it's good to get the end users or the buyers' perspective of what are meaningful benchmarks to them. So I would say that this group may want to try to engage with some end users so that they can express their perspective on what they would like to see as benchmarks that would be useful to them in making investment decisions. And so that can also be a stimulus for people to use those benchmarks. So you have to have different kinds of carrots throughout. Publications is one. I think that's always a good one, but also the potential of enticing a purchase.
Along those same lines, I would think that the goal would be that the consumer, the user, we would want them to ask, has this been benchmarked? We want them to say, okay, we'll prove you can do X, Y, Z if you're saying that you can. The more they're on board, the more regular that is, then the more adoption will happen. I also wanted to say that what I've seen reasonably effective, especially lately, at making sure these benchmarks get out there and accepted is actually competitions of various sorts, because people who are just interested in watching get to see what the tasks are, get to see what the benchmark tasks actually are, but then also you get companies and teams competing with each other. And so their goal is a little bit more, as Elena would say, there's a carrot, right? There's some maybe money involved where they're a lot more interested in meeting this benchmark. And so it's pushing technology. And if the competition lines directly with some standard object or standard reference material, then there's perfect collaboration between the competitors, what they're actually doing, and the benchmark that they're achieving.
And as Kenny will talk about very shortly regarding the NIST task boards, that's exactly why we started doing the IROS grasping and manipulation challenge, was to raise awareness to our assembly task boards and metrics associated with those. Okay, does anyone else want to comment on Burke's discussion topic, or could we move on to Kenny? And I guess we're getting, I didn't think we'd use up 3 hours, but it looks like we're getting pretty close. Kenny, are you ready to present on the NIST task boards?
I am. Can I take the screen?
You sure can. Thanks, Burke.
So let's This one. Okay, can everybody see that okay? Yeah? Okay, I got a thumbs up. So I'll try to be quick. I know we're kind of nearing the end. I'll leave plenty of time to engage in more discussion. So just real quick, I'll be talking about the benchmarking protocols for evaluating small parts robotic assembly systems. I already kind of gave you a background about me, 6+ years doing testing in some manner of robots, and then 2 years working specifically on these actual task boards. This is an introduction about the background, why we need the NIST assembly task boards. I'm not gonna read through that because that's a mouthful, and because we've kind of already touched a lot, and most of you guys are aware of what the issues are, aware of why these things need to be out there. So a little bit there, and then so let's get into the meat of it. What are the task boards that we have so far? So there's they're called assembly task boards. So hopefully, if this nomenclature gets adopted, we can just call them ATB or NIST ATB assembly task board. And we have so far 3 of them. One of them, figure 1, which is based around peg insertions and connections. That is the one that NERV has available for purchase. That's the one that's been most widely adopted so far. But there is 2 more. There's a belt drives assembly, and that's got 3 different kinds of belts: a chain, and a round belt, and then a timing belt. And then figure 3 shows kind of wire handling or cable routing. And that one, which we'll get into, stems into some future task boards. So what's the protocol? Why? How do you actually use these task boards? We like to start, it's the same as you would see in a competition. Start with disassembly. Take the board apart, remove each of the parts and put them in a bin. And then secondarily, reassemble the task board using something that we would call like a kit tray or kit layout, where the parts are already in predetermined positions. In the bottom right, you can see what that kit mat looks like. Underneath each of those objects is a drawn image of that object, so it's clear where it's supposed to be and what orientation. And the goal would be that the team or whoever would take the objects from those locations and insert them back into the task board. So more about specifically task board 1. There are 4 cylindrical pegs of varying sizes, from 4 up to 16, and then there are 4 square and rectangular pegs, also from 4 up to 16 millimeters. Then there's threaded nuts, where you screw the nut onto a screw that has already been attached to the task board. And just to kind of stick with the theme, those are also 4, 8, 12, and 16 millimeters. And then there's meshing gears. You can see the examples in the bottom right of how teams might achieve some points or partial points, and then they might achieve full points if the gears are actually meshed and the gear has been pushed, seated with the board. Additional, which are not included necessarily in these pictures, additional tasks are the orientationally specific connectors, like a BNC cable or a USB or Ethernet, and then a couple others. So NIST Task Board 2, the belt drive, these images are from a competition board. So you might have seen the first image. That was a better layout of each of the 3 belts. But what's neat about this one is it's actual assembly of something that people can relate to. There are belt drives out there. So it doesn't just involve more elementary tests like what kind of objects can the robot handle, or maybe whether or not they can handle flexible parts, whether or not they use 2-hand manipulation. But because this is an assembly that somebody can relate to, an actual belt drive assembly, there's tasks everywhere in between where they might have to put the pulley onto the peg with some kind of spacer like a metal collar, and then thread a nut to hold that pulley there. And then maybe they have to bring in the belt and all the actions that are involved in tracking that belt on the pulleys and making sure that it's been tensioned. There's 3 different kinds of tensioners in the belt assembly based on the belt that tensioner requires. The third task board, TB3, is a cable routing task board. And again, this is an image from a competition board that takes just the basics of what that task board has. If you're looking at it from, I'll say front to back, which I can show you another image later, the idea is that it gets progressively more difficult to handle the cables. There are 3 cables. One of them is a audio jack cable. Another one is like a stiffer Ethernet cable, much thicker. And then the last one is like a SATA flat cable that you might see inside the belly of a computer. And first they would track around pegs, relatively simple, and then maybe they would place them accurately within clips and close the clips, and then feed them through channels, which you see in the image. Previous versions of the task board didn't have these little slots cut, so it might literally require two-hand manipulation to feed the cable through the channel and then regrasp it on the other side, which may involve losing vision of the end of that cable, which could be tremendously difficult. So this is definitely one of the more difficult task boards. The first step so far has been opening up those channels to maybe dial it back a little bit, maybe kind of meet industry a little bit better, see what they can do, and then maybe grow from there. So some of the design reasoning behind at least the first task board, mostly the first task board, but also this kind of helps us formulate our ideas for all of the future task boards. There's a book called The Product Design for Manufacture and Assembly by Boothroyd and Dewhurst and Knight, where what they do is they measure how long it takes a person to do a specific task in industry. For instance, pick up a peg, handle a peg of a certain size, and then insert it in a hole. Those times have been recorded. How long does it take a human with their dexterity to do each of these specific tasks? And it goes from peg insertions all the way up to wire handling. It actually does some wire handling, manipulating and closing and opening clips, or even soldering. So I definitely see future use of this for if we get into, maybe more complex task boards. You can see on the left is an example of a comparison between maybe how the human does the tables that they provide in the book, and somebody who's using these task boards might bring right alongside these task boards. Okay, my robot did the, let's say, less than 6mm peg handling in 15 seconds, which is 15 times more than the 1.8 seconds that the human took to do that task. It can be very useful for cross comparison between what a person can do and what a robot can do. So this is kind of a little bit what I was talking about earlier about the competitions, promoting the task boards, but also promoting teams and industry to solve these problems. The top right image is what I call a combined task board, which we use for the competition, that takes in consideration each of the previous task boards that I talked about, the peg insertions with the gears and meshing, and then this one, it kind of does the inverse of the nuts. It actually has the screws that we're threading into the board. And then you can see the belt drive and the cable routing. So far, we've had competitions probably before 2017, but before that, I was not involved, so I can only quote up to 2017. IROS, and then WRS 2018, IROS 2019, and then very recently, this month was the IROS 2020 virtual competition, where teams did almost exactly the board that you see in the top right. There were some changes made, and it was nice to see teams come out pretty successful at doing these tasks. And in previous competitions, the bottom right image shows that they took the belt drive that we had as a task board and they implemented it into an assembly where teams had to put it together such that at the end, it actually ran. Right? It would be attached to a pulley system with a cable, and maybe there's a weight on the table that if it ran correctly, the weight would be lifted to prove success. So we've seen all kinds of solutions out there. there's been previously a lot of expedient lead-through programming, which is nice and it's user-friendly. But even that is a rather simple approach and has a lot of fallacies, especially if the task itself shifts. You can imagine if you taught all those points on that task board and then you move the task board even an inch, now you got to teach them all again. There's a lot of problems with doing lead-through programming. So thankfully, we have seen teams start to adopt and incorporate CAD data and AI perception and using cameras to observe and identify objects, and then figure out where the hole is and understand what is negative space, what is positive space, and how to interact with those. And they, like I said earlier, teams have started to prove competency on these task boards. So I think that's a really good sign. We've gotten a lot of feedback. That's not a bad thing. We have a lot of room for improvement. We're willing to accept that. This is just some of it. There's a much larger list of ideas that we want to implement already being done task boards, all the ones that have already been produced, edits that need to be made, and that's great. We're welcome to take as much feedback as you have. But there's also some ideas for future benchmarks. What are the task boards that still have yet to be produced, and what kind of competencies would we like to tackle? Some of which might be a two-hand manipulation specific task, or maybe manipulating flexible materials, something that can squish and move like a plastic bag, or maybe a rope, something you can tie a knot with. And so far we've dealt strictly with horizontal task boards, but we designed them with these 4-corner holes that allow somebody to mount the task board in any orientation. We would love to see people do it upside down, for example, or vertically. But that may be future competitions. I can say that so far we already have plans for a wire harness. This is slightly different than the cable routing. They do kind of piggyback off of each other, but the wire harness directly out of industry would be a robot, quite literally designing a wire harness so that at the end they can grab the harness of wires and they can pull it out of the task board, and they have a finished result of cable that has been tagged together, and it goes through the body of a computer, for example, or through some machine that they might need a wire harness for. And then there's been some talk of a vision-specific task board, something that maybe has a lot of objects of very similar shape and size, so it's difficult for point clouds to decipher between one object or another. Maybe there's some negative space, or there's reflective surfaces, which cause other issues. And again, that's still in development, so we'll take some feedback on that one as well. And here's some resources, and that's it. Thank you.
Thanks, Kenny. So yeah, so right, we promote the use of CAD data, force control, perception. We try to keep folks away from using lead-through programming. Typically, with the judge takes during a competition, judge takes the competition board and places it somewhat randomly on the workspace, so the teams don't know where it's located initially, and they have a full CAD model of the task board. So if they, typically get to work with a practice task board, the competition task board has parts located differently. So what they can do is as soon as the competition starts, they can parse the CAD data and determine the locations of parts on the task board. In addition, they can affix markers to the task board to locate the task board within the work volume and work from there. And so as people began to realize that, these are the kinds of, this is manufacturing oriented. Most of the work NIST does is manufacturing oriented. I think universities, these mostly researchers, up and coming researchers, begin to realize, what is available in a manufacturing environment to help with robotic assembly, such as CAD data, and how, what the environment is like, and things change, and you can't depend on fixed fixed objects because that leads to cost. Fixturing is very expensive, much more expensive than the robot system itself. And if you have multiple batches of product, you can't keep changing things around. As far as fixturing becomes too costly to implement a robotic solution the old way. So we need to focus on sensing and use of engineering data. Anyway, thanks a lot, Kenny.
Thank you.
So we have about 5 minutes left in our meeting. First, thanks everyone for joining us. I hope that you stay involved. This is just a kickoff meeting. We are going to take off on the NIST performance measures. That's our first standards effort. I'd like to try to get some feedback. I'll send out an email to everyone who is involved in this meeting. First of all, if you have any colleagues that might be interested in this work, please send them to me and I'll add them to our mail list. And what I'll do is I'll start asking people to, who's going to volunteer to help, who has, bigger interest in certain measurements, solutions, such as Lionel from Canada, said he was interested in a couple of the topics and was willing to help spearhead them. So I'm looking for more people to step up. NIST will be there to help you, guide you, but we just don't want to do it all because it's just not the right way to develop a standard. So based on what we have today, I'll send out an email. I'll send you the link for the recording, right, Kenny? We're recording the meeting.
Yeah.
So you can forward that to any colleagues that might be interested that missed the meeting. And then we'll take it from there. And I hope that you can participate in more virtual meetings. Maybe someday we'll meet at a actual conference of the sorts. We'll see. It might be a year from now, but we'll do it. Anyway, any last minute comments? Feel free. We have 4 minutes left. Okay. So again, thanks for joining us, and we'll stay in touch. And I'll keep bugging you. So you're on my mail list now. All right. Thanks, everybody. Take care.
Thank you. Bye-bye.
Thank you, Joe.
Thank you. Bye.
Bye.
Thanks. Bye. 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 Bye.